Okay, we'll get started. Welcome back, everyone. It's my honor and pleasure to introduce Alvaro Pascual-Leone to all of you. He is really very much the world's leader in the study and application of procedures for neuromodulation, which are becoming increasingly important in both basic research to interrogate the functioning of the human brain, as well as in its clinical application. Alvaro received his MD and PhD in Germany, in Freiburg, and he has been associated with institutions both in Europe and the US. He did his neurology training in Minnesota, then went to NIH, was at NINDS for a while, and went to Harvard in 1997. His work is really replete with a mixture of both basic and clinical research. He also has done an enormous amount to standardize and propose guidelines for the use of techniques of neuromodulation in human clinical applications and in research. I first really became super excited about his work in the 1990s when he did some really pioneering work on the effects of rapid transcranial magnetic stimulation that was presented in a lateralized way to dorsolateral prefrontal cortex in its application to treatment-resistant depression. And that was really early and very creative work that really presaged the increase in interest in using neuromodulation as a treatment strategy for intractable depression. And he has focused on a variety of neuropsychiatric disorders, ranging from blindness to psychiatric disorders. And all of this has been with a real interest in the study of brain plasticity. So we're in for a treat today, and I'm super thrilled that Alvaro is here with us today. So thank you, Alvaro.
Well, thank you for having me. It's oh, I forgot this. There you go. Does it work? Yeah. Thank you. So thank you for having me. It really is a great pleasure. I've enjoyed the morning, so hopefully I can keep up the momentum. I think what I would like to tell you, share some results and some experiments with the underlying theme being that sometimes having a tool is actually necessary and a great opportunity to revisit theory. We like to think that we have a theory and look for a tool. I'm going to argue that sometimes it's sort of the other way around, that having the tool actually should call into question the theories that we hold dear to our heart and offers an opportunity to actually revisit it. And in that setting, we have the beginnings of a way to read and write the brain non-invasively, and that offers opportunities both to translation to clinic, but also for fundamental wonderings about how the brain behavior is organized. These are my disclosures. They're relevant today, particularly because I will tell you a little bit about Linus Health and about TI solutions. So I'll disclose again when the moment comes. But anyway, that they are. I'm a still practicing neurologist, and I do a lot of time devote my focus and attention to research. I've had the privilege of serving as a Dean for Translational Research at Harvard, and the usual way we think of that effort to translate insight from research to clinic is in that order. You do the research, and then you figure out what patients could benefit from it and seek to translate it. At least in neurology, that has been rather arduous way to be kind. When things have translated, they generally are serendipitous translations. We didn't really mean that, but it turns out it works. It's awesome, but it's sort of counter to the approach. So part of what I'm going to try to argue is that we need to flip it. Not saying exclude this path, but add another that starts with the clinic, characterizes the patients in their problems and uses then a sort of clinic-guided reverse engineering. We have the tools for that to actually then question and ask what are the fundamental mechanisms to bring it back to the clinic. That requires a sort of precision medicine and of one approach where we focus on the symptoms, the disabilities, rather than necessarily the labels we like to give it, that we capture not just the behavior, but the physiological substrates of that behavior, that we personalize the intervention, and then we keep measuring the impact to have ultimately a closed loop thing. And I think the talks this morning, both of them illustrated this, I think, in a beautiful way. So thank you both for that. The way I've been thinking about it is that in the setting of health, we have a certain brain structure that gives rise to a certain pattern of brain function. Tends to be complicated as heck, but we can simplify it to some degree and identify spatio-temporal signatures and symbols of neurons that are the building blocks, really, the unitary functional element of the brain. And there is a spatio-temporal signature that maps onto every emotion, every thought, every behavior. They're dynamic, they're flexible, they're plastic, they're identifiable using tools that we have to our disposal, and I try to illustrate that. In disease, be it because of a stressor, an injury, an insult, or whatever pathological process, there is a structural or functional change. It sort of doesn't matter because of the end of the day, function is structure, structure is function, as Lakatos used to say. And so the net result of it is that there is some alteration of spatial-temporal signature, and those are the proximal representations of symptoms or disabilities. What I'm going to try to argue is that if you frame it that way, then brain-related disabilities are ultimately, by definition, alterations of spatio-temporal signatures that capture circuitopathies. They capture alterations of circuits. We may know what circuit it is, we may not, we may guess, we may be wrong, but we might be able to approach it by control perturbations disrupting that spatio-temporal signature, and sometimes it may translate into symptomatic improvements, which may have therapeutic opportunities. And if it is true that function and structure are bidirectional things, then by force controlling or normalizing a spatio-temporal signature, there might be an upstream effect on the pathology itself. And I'll try to illustrate some of this. Now, there is a lot of methods for non-invasive brain stimulation. There are some electromagnetic. Now we know that a magnet, if it's strong enough, can modify cortical excitability, and they have a neuromodulatory effect on its own. You better be careful in handling those magnets. We did some experiments in the lab. They're 3 Tesla little things, but 3 Tesla. You don't handle it with care, they will attract each other. If they attract each other and your postdoc's little finger happens to be in the close by vicinity, it may just chop it off, which actually happened, and it's not a joke. It's just to illustrate the fact that they're strong magnets, but they have an effect by holding it in place. There is light that has an effect, sound has an effect and has a lot of appeal. Even sensory stimulation from the periphery is being explored. Neurologists dealing with dementia patients, Cognito is a company that uses, based on work from Li Hui Zai and Ed Boyden, sensory stimulation inducing gamma activity to try to improve cognitive function. So there's lots of methods of non-invasive brain stimulation. I'm going to focus on two because they're the only ones that I feel like I can really speak to in a sort of at least knowing what I'm talking about kind of way. The transcranial magnetic stimulation and transcranial current stimulation, the latter being really a family of methods. Sometimes useful to think about the history of these things a little bit. So let me start there. If you haven't visited the Royal Society in London and you have the opportunity, it might be worth a trip there. Michael Faraday is the man credited with discovering electromagnetic induction. And on a given day, the 29th of August of 1831, he wrote a letter to a friend saying, and I quote, "I think I got hold of a good thing." And what he described in his letter that you can still visit, that's a picture of it, is a little experiment that many of us were taught in physics. If you have a cable and there's a current passing through it, there will be the current going like this and a magnetic field, some freaking force that will be generated around it. And if you have another wire close by, that magnetic field will induce a current, bridging the gap of space, and you can pick it up on the other side. And he demonstrated that with that experiment where a copper wire A is looped around one side of an iron ring, and a current is picked up after passing through A in a second wire B. He was a good experimenter, so he asked the question, well, maybe it's because of the iron ring. So he cut the iron ring in a subsequent experiment. It still was passing. He then took the iron ring out. So it's not the iron core, it's the wire that has it. He then went on to separate the wires. So there is a distance relationship, change the orientation. There is an orientation relationship, exquisitely beautifully done experiments. And of course, it took 150 years for us to actually figure out we can maybe use it in the brain if we just figure out how to do something that he had pointed out, which is the critical thing about this is not how big a magnetic field you generate, but how quickly it changes with time. It's the time derivative of the magnetic field that determines electromagnetic induction. And for that, you need to pass the current through the first coil really, really quickly. And Tony Barker figured out a thyristor, an electronic switch, might be the way to do that. Take a current in a capacitor in a matter of milliseconds into a coil. That allowed one stimulus at a time because it needed to recharge the capacitors. John Cadwell figured out ways to have parallel capacitors charging and discharging so that it was possible to do repetitive stimulation. And then I was privileged to be part of a study that Richard was just mentioning, where we tried to apply this to try to modify activity in the prefrontal cortex in patients with depression. Won't go into the why, that there's a whole story. There was a lot of data, among others, his own, as to why that might be a reasonable target. But I want to share one thing about it to illustrate the challenges of research. I think back on this study and think, what were we thinking? These were really sick people. We were doing multiple crossover studies. It was nuts. I can't believe it worked. But one thing that the IRB contributed was the following. So we set up the study to say, we're going to do a number of sessions, and we're going to do multiple days in a row. That's what the safety had been done so far, so that's what we're going to do. And they said, okay, how are you going to get them into the lab on Saturday and Sunday? We said, well, it's okay. The back door of the building is open, so we'll bring them through the back door. And they said, yeah, that works, except these are really sick people with the psychotic depression, some of them, and the back door goes by the morgue, and you can't do that. So we said, okay, well, how about we skip Saturday and Sunday? Yeah, you can do that. And so that became Monday to Friday into subsequent weeks. But again, there is a lot of serendipities and chance occurrences in clinical trials that I think is worth highlighting and be aware of, because otherwise you fall trapped to the fact that it turns out that Monday is a particularly predictive day of whether you're going to respond or not when you analyze the data. the first Monday after the break. And so it's easy to say, oh, we wanted that. It allows for consolidation. We did not. It was completely imposed by, anyway. Similarly, eventually, different devices got pivotal studies done, FDA approval. You can see the timeline. I think it's always worth remembering that it takes a very long time to get to something that is actually clinically established, useful, and applied. And even at that point, adoption by practitioners lags behind. Now, from the very beginning, we've known that magnetic stimulation, transcranial magnetic stimulation, reaches a target in the brain, but it's not limited to that target in the brain. If you think about it, if I apply a stimulus to the motor cortex, my hand twitches. There is at least 2 synaptic steps between that cortex and the muscle twitch. So when people say the effects of TMS are local, it's like, really? I mean, who looks at the data and thinks that way? It's always a circuit effect by definition. And elegantly, Tony Valero showed in cats that you can target a given area, say the visual-parietal cortex, and show that there is a local impact on metabolic activity in this case, or neurophysiologic activity. Depends on how you look at it. This is FDG PET. But you can see an impact here at the targeted location and a remote impact right there, a punched out kind of effect that has to do with the richness of connection between the splenial visual cortex and the visual-parietal cortex, connections that happen to be excitatory. And so if you suppress activity in the targeted area, you suppress activity remotely. Tony showed that if you look at the strength of connections and their sign, you have a network impact that you can demonstrate in vivo in the cat, and we can in human, that is predicted by the knowledge of those connections. So think of TMS as a tool for impacting, perturbing a given location in the brain and having an impact along a circuit of the brain that we'll want to figure out what determines that impact in more detail. Transcranial current stimulation, on the other hand, is very different. Also goes back to Faraday. In fact, we call it Faradizing the brain. It's not electromagnetic induction. It's applying a steady, very, very much lower current. In TMS, 8,000 amperes. In TCS, 1 to 2 milliamperes. So 1 million times lower. But either as a steady direct current or as some form of oscillatory with lots of oscillation frequencies or with one picked one. Transcranial direct current refers to the steady current, transcranial alternating current to the specific oscillation. The different mechanisms of actions that we assume are at play, how certain we are is not completely clear. But it also allows to combine some of them, and I'll tell you some of those experiments in a second. The one thing that is nice about it is that it allows to do the stimulation in a rather multifocal way. You can generate a field that not only targets one specific location, but by design targets most or much of a network distribution. So if you think spatio-temporal signatures as being patterns of activity, if you think about it, if I have 128 channels of EEG on the given subject, I don't know where the source comes from, but I don't need to know. All I need to know is that I can pick up that current, flip the induction, and instead of registering, inject. And if I inject with the same amounts, proportional to each other, as I pick up the signal, I'm going to get to whatever source it is, even if I don't know the source. That's sort of the logic behind it. So it's a way to potentially, with algorithmic calculation, generate fields, electric fields, that match patterns of activity in the brain. Does that work? Is that better than targeting one spot in the brain? So David Fisher asked that question and showed that if you record brain activity with EEG and define a given pattern of activity associated with a given motor task, and then you apply stimulation either focally to one motor cortex or to both motor cortices or to the entire motor network of both hemispheres. You can show in the little graph below that in the case of this network stimulation, you get a greater impact that is more distributed and affects both hemibodies. So one way to think about brain stimulation then is that it is a way to control a perturbation to the brain. And I like to think of it as sort of perturbation biomarkers. And in physics, there is this notion of a toy model, the idea that if a system is very, very complicated, but you can identify a by design simplistic way to think about it, you may gain valuable insights. And so we've been playing with this notion of toy models of brain behavior relationship or brain responses to stressors, insults, and so forth, using TMS as a control perturbation to the brain and picking up the response of the brain. So the nice thing about that approach is that you can do the exact same perturbation in a mouse, in a rat, in a cat, in a child, in an adult, as long as you know exactly what field you're capturing. This is not trivial, but at least fundamentally, you have the possibility of doing that perturbation in the same kind of way. So it's a potentially really translatable phenotype. Alex Rothenberg, for example, approached in rats the idea, can we look at the efficacy of the mechanisms of plasticity in vivo in a similar way as we would do in a slice preparation? So you apply a stimulus, perturbation, you apply a train of stimuli to modify the response, you check again the response to the stimulus. And if you record the response after an intermittent pattern of stimulation in between, you get a potentiation of response that is apparently absent in AD model animals, Alzheimer's disease model animals, selectively for the potentiation. So the idea is you record the response to the perturbation, you apply a train of stimuli, and you record the response to the perturbation again afterwards. And depending on the pattern of stimuli in a slice, you would expect a similar response. In vivo, you might be able to get at the efficacy of the mechanisms of plasticity in animals, Alex was showing, and maybe in humans. And indeed, you get an LTP-like or an LTD-like response that we can characterize, and we can show how it changes across the lifespan. Katerina Freitas has done that and shown that we're all on a steady down slope of mechanisms of plasticity becoming progressively less efficient. But there's always there's always a capacity. But if you know what slope you're in, then you can identify deviations from that slope from a given individual and identify, for example, very, very early on, an alteration of the efficacy of the mechanisms of plasticity in folks who then, when checked, turn out to be having Alzheimer's disease that is not just symptomatic. And so there is an early alteration of efficacy of mechanisms of plasticity that allows to identify physiologic biomarkers that can potentially indicate disease. And the cool thing about this is that it is very specific for a given network. Remember the work from Tony Valero I mentioned is specific to the connections. Davide Momi has shown in humans the same type of relationship. You can demonstrate a given pattern of response that is different for DMN versus DAN or any one network. It remains specific by network, by subject. And consistent with that specificity of the response of the perturbation, there is a relationship between the type of response you get and the behavioral manifestation of that activity in that network. So for example, Maria Redondo Camoses has done her thesis showing that frontoparietal connectivity is related to cognitive function in predictable, measurable ways, and the strength of the connectivity is truly a marker of effective connectivity relevant to behavior because it relates to the behavioral manifestation. Now, we wondered about the question, how consistent are these measures across subjects? And so Recep Özdemir was trying to set up an experiment to do multiple measures in different areas in different subjects to try to ask the question, is there a fair amount of test-retest reliability? Can we rely on these things? And in exploring this, I think he sort of accidentally, frankly, came upon a rather nice result, which is that if you take at least 3 measures in any one of us, then you get a pattern of response that not only is it reproducible within subject, it is unique. It is a real brain fingerprint of any one of us. It's very variable across individuals, very reproducible within a given individual. And what that allows us to do is to have a sort of physiologic fingerprint that one can really track and see deviations. If you have a bad night's sleep, if you take more medication than you should, or if you start developing a given pathology. So a way to monitor individual responses at the brain level. We've been wondering, and I've been trying to play around with the idea, how can we capture similar fingerprinting, but of behavior to correlate it with it? And again, I loved Olu's talk because of similar sort of motivation of thinking. Linus Health that I mentioned briefly is a platform to capture multimodal signals. So gesture, posture, gait, fine motor control, speech, performance in drawing, in such a way that we can extract metrics from those measures and analyze what neuropsychologists would call the Boston process approach. So not simply look at the end product of your performance of a given task, but the way you go about doing it. Instead of looking at whether or not at the end of 3 minutes you produce normal clocks, in this case, both subjects did, capturing 1,400 metrics, in this case, of your drawing process, and then asking the question through AI and machine learning, is there anything that predicts at the individual level whether or not they have cognitive impairment by full neuropsych testing, whether or not they have amyloid in the brain by PET studies? The answer could have been no, but it turns out you can generate AI engines to predict not only cognitive impairment, but function in activities of daily living, amyloid or tau status. Of course, these are all different engines. These are all banking on different metrics, but they're all captured in real time at the same time out of a 3-minute task that asks you to say a sentence and draw a clock. And we're capturing eye movements and voice and drawing performance. And somebody asked earlier, and we've looked at the question, can we predict risk of further decline? And if you have enough subjects and follow them, Framingham Heart Study has done that, and the Rush population study has done that, and looking at one as a learning and the other as a test cohort, we were able to find that we can predict the development of dementia with 5 years, or signs of MCI or dementia with 5 years of anticipation. So I think we have tools to characterize physiologic both fingerprints and behavioral fingerprints if we leverage technology. And what that allows us to do in thinking of translating it to clinic is not be reactive about neurological and psychiatric diseases and not wait until symptoms are so prominent that the family complains and we finally give in and go see somebody, but rather identify the individual deviation of the trajectory. And the moment there is a significant deviation, lead to early detection and hopefully early intervention, ultimately preventing the disability rather than trying to cope with it. If we don't do that, by the way, what we're accomplishing right now is we're very good as neurologists, I think as psychiatrists too, at having people cope with disability, live with it. Right now, 9 out of 12 months of extended lifespan is disability prone. Neurological and psychiatric diseases together are the number 1 cause of disability worldwide, more than cancer and cardiovascular diseases together. And yet, I'm at least pointing to the fact that we have the beginnings of tools to identify the individual fingerprint, to detect an individual deviation, and in doing so, to predict and stratify not only for clinical trials, but for therapeutic interventions in clinic, who is going to be healthy and who is in need for interventions. Let me show you that this actually works, if I may. Kilian Avellaneda did this study working off findings from Mark Eldaev from a number of years ago. Basically, you apply a perturbation to the angular gyrus, and you measure the impact. That's what Mark wanted to do. Can we characterize the connectivity response? And what you get is that you get essentially data-driven 2 clusters of people. Some have this in response to the target area. This is the average, but some folks behave like this with a lot of frontal reactivity in response to the stimulus to the parietal cortex. Others have very little. Turns out, in part, this is age-driven. But the question was, okay, so if you forget about age and you look at how these people do 3 years later, 5 years later, how are they doing? It turns out, Kilian showed that for any number of tasks, this is phonemic fluency, but you can look at the same way at other neuropsychological testing, and I think it's more broadly cognitive function. What he found is that the ones who responded with less frontal activity were worse off afterwards, whereas the ones that had a more young-like response regarding of their age, more activity frontally, more connectivity, were cognitively not only better, not only the same or not worse, but oftentimes better. So we can anticipate something. We have no idea what this means, really, other than there is some difference in the working and connectivity of the brain response to a control perturbation that anticipates some behavioral consequences. Leveraging COVID and an ongoing cohort study in Barcelona, Rubén Perellón asked a related question. We had these measures of TMS, EEG that I've been talking about. And then we had done this study for 3 years before COVID hit. We had waves of assessments, and then COVID hit. And in Spain, everything shut down. And people were asked to be in their homes, and they couldn't go into the garage and to potentially interact with each other. And the police was watching. And there was a lot of stress, understandably, as we had here. And there was any number of mental health consequences, among others, an overall worsening of mood and stress. And you can capture it a number of different ways. This is, for simplicity's sake, just a PHQ-4 measure. And you can see that of the population, some people got worse and some people actually got better. Some people were happy to not have to go outside, thank you very much. And others were very stressed by it. And of course, there were a lot of other fears. What Rubén did was look at the responses 3 years prior in response to frontal or parietal TMS in a controlled way. Can they predict the outcome of this stress associated with the pandemic? What he found is that those who are, quote, resilient, they didn't get worse mood-wise and in fact got better, had a given pattern of response that looked very, very different from those who were vulnerable. And the frontoparietal connectivity, again, that I was mentioning from dorsolateral prefrontal cortex, in this case, not from parietal, predicted the stress reaction and the mood consequences of it. So just 2 simple examples to illustrate that notion that perturbation biomarkers are capturing something fundamental about individual subjects' brain function that can be predictive of behavioral consequences, including of disease symptoms in the setting of pathology. hopefully is illustrated with those examples. Now we have tools to know not only where am I holding the coil on the head, but where am I targeting in the subject's brain? We have image-guided neuronavigation systems. We have robotized systems that allow us to make sure that we define a given target in the brain, and when the robot finds it, it applies the stimulus, and only then it applies the stimulus. So we have ways to be quite precise in the targeted location. That's sometimes great and sometimes problematic. If you know exactly where this bottle is, it's great to know where to drop the water. If you don't know exactly where it is, it's a great way to miss the water, right? So it's not necessarily solving a problem. It's a tool to potentially ask specific questions. But thanks to those tools, we can be exquisitely precise to the point that we have FDA approval for motor and language mapping outside surgery, predicting the surgical PEMFIL-like cortical mapping. And we have a number of tools that are approved or cleared by the FDA for various diseases, and an even longer list of applications that one can call off-label, where there is at least more than 3 independent control studies showing support. So that's great. So we have tools that allow us to ask specific and fundamental questions about the brain, and I would argue we have tools, the same tools, that are actually making a clinical impact. Back of the envelope sort of calculation, if you just think medication-resistant depression, assuming from what we know about 600 is a conservative number, 600 systems in clinical use in the US, there is 25 patients going into remission by day with medication-refractory depression, where normally less than 4% would go into remission overall. So this has a real clinical impact. And if you respond, we know that you have months of response. We know that 90% of patients, if they responded the first time, will respond again subsequent times. We know that it is possible to use maintenance to maintain it. It's exciting. We can help patients today with these tools. And yet, want to shift gears, we're only at the beginning. There is an enormous number of questions that we have no freaking idea about. Among others, this whole therapeutic application in depression is predicated by a hypothesis, which Mark George and I and others put out, saying, we're changing cortical excitability, except we eventually got an NIH grant to measure cortical excitability and see how much of the therapeutic response is due to the change in cortical excitability, and it's negligible. So there is a change in cortical excitability, and there is a therapeutic response, but it's not explaining, one is not explaining the other. So mechanistically, we still don't quite understand what the heck we're doing. I think the most important thing is that I believe we are not really realizing the promise of neuromodulation. So I like the idea of the glass because of the following idea. If I want to fill this bottle of water, and if it's true that spatio-temporal signatures are the substrate of these abilities, you can think of spatio-temporal signatures as this bottle of water. If I know exactly where the bottle of water is, I should be able to put a dropper here, fill it out to the right amount, and be precise, no side effects. Instead, what we're doing on a good day is opening the ceiling sort of in this neighborhood, letting it pour here. You fill up the glass of water, you get me completely soaked, that the television stops working. We call it unavoidable side effects, and we're perfectly happy. That's what we're doing in medicine right now, in neurology right now, I think. So we have to think about it differently. We have to think about it really leveraging the possibility of potentially localizing this bottle. And I want to talk a little bit and mention a few challenges and opportunities in that regard. So how do we actually test this notion? It may be wrong, but there is a lot of data in support of this idea of circuitopathies accounting for disabilities and symptoms as the substrate. So how can we get there? So the first thing that we need to realize is that the effects of the brain stimulation, the physiologic effects, can be enormously variable across different individuals, across different moments in times in a given individual. At the very least, that means we need a lot more responses measured. For example, we generally say that low-frequency stimulation to a given area is inhibitory, and it's become so engraved that people say, I apply inhibitory TMS, or I apply inhibitory TDCS. There is no such thing as inhibitory TMS. It doesn't exist. There's nothing fundamentally making it inhibitory. Number one. Number two, what you're calling inhibition is not physiologically inhibition. On a good day is lack of facilitation. And if you actually measure the effects, you get this stuff. 1 hertz in some people is excitatory, in others is inhibitory, in others does absolutely nothing. You bring these people back the next day and it's flipped. There is no within subject reliability. It's a crapshoot to know what it's doing at a physiologic level, unless you do the experiments of Recep or Zemir and systematically look at it multiple times, and then you have consistency. But the bottom line is we need to measure the effect. We can't rely on it. If what you want to do is actually increase excitability, measure it and establish whether you're increasing it or not. So we should really couple it with some sort of monitoring, not for good, that's not scalable at the translational clinical level, but for understanding what we're trying to do, I think it is. So that's the first idea. The second idea is that brain stimulation is always an interaction with what it finds in the brain. And we generally call it noise, and so apply the same parameters, and sometimes it works one way and another. But there is another approach, which is to leverage the state dependency effects. And the person who introduced that notion has been arguing for it, among others, is Juha Silvanto. Juha did a very cool experiment that I frankly didn't believe was going to work for him, and so I told him it's a bad idea. And he said, okay, will you bear with me doing it? And sure, go for it. So what he did was built on work that Estrella Gomez had done. There is an area in the brain, you'll know, MTB5, that has neurons that code for direction of movement, visual area in different directions. There is population of cells, it's Newsom and others have very clearly characterized it. You apply TMS there, and you block the ability to detect motion. You induce an akinetopsia transiently. Estrella had shown it, Semir Zeki in London had reproduced it, it was pretty clear. And Juha said, what about if we set the state in such a way that certain cells in that area are in a different place than the others? What about if you look at a moving dot kinetogram for some period of time so that you attenuate the cells that code in this direction and only those in this direction? And now I apply TMS. What happens then to your movement detection? TMS is fairly non-specific. It's a perturbation. It's going to affect all neurons, but the neurons are not in the same state. And what you have found is that when you do that, the cells, the direction of movement coded by the cells who have been adapted, it behaves completely the opposite way than the cells that have not been adapted. Those that have been adapted get better after the TMS instead of being disrupted. Those who have not been adapted get disrupted. To me, the obvious take-home message from this rather old experiment, but not really translated systematically, is that we should be leveraging state dependency. We shouldn't let them do whatever they want. We should control what they do and turn it into an experiment and find out what is the best intervention that gets a given effect for each of us. That's the precision approach. So leverage state dependency. attempts to do that have actually been made. There's a company that famously went bankrupt that tried to do that. Don't go bankrupt, but still do it. What they did was combine brain stimulation with cognitive tasks in patients with dementia. So I engage you in a given cognitive task that by imaging we know engages a given circuit in the brain. I target the stimulation in that context. I'm going to have a state dependency, quote unquote, mediated enhancement. It turned out it worked. You look at the data that published, it worked, except the company was running into money problems. And because they were running into money problems, they decided to ask the FDA for permission to expand the indication and allow patients with more severe Alzheimer's disease to be included. FDA said yes. Nobody with a more severe cognitive deficit responded to any intervention. The overall statistical effect was no longer positive. The FDA said, you missed your endpoint. The company said, yes, we did, but can we talk? They said, we can talk. It's going to cost you this much, and they went bankrupt. But it illustrates, again, the challenges of this and the possibility of the intervention. So lots of questions behind it, don't get me wrong, but how do we create the optimal state? I have no idea, but I hope some of you do. When do we couple it? Do we do the stimulation before, during, after, some hours later? There's a lot of questions to be asked. But we're not even asking some of these questions, which my point is it fails to make a possibility of realizing the promise of brain stimulation. One last point along those lines. Let me illustrate it with a case along the lines of the N of 1. This is a patient 10 years after a stroke. It is a very large MCI stroke, leaving him with significant, very classic non-fluent aphasia, studied by Marnie Nisser, a speech pathologist. When he tries to speak, this is the pattern of activity you get. A lot of activation in the non-dominant hemisphere and damaged hemisphere, and often put forward hypothesis was the right hemisphere compensates. He's recovered what he's recovered thanks to that compensatory activity. With Marnie, with the support of NIH, we did a study asking the question, what areas here can you disrupt, targeting by the imaging, and make him either speak better or worse? What areas lead to a speech arrest? This person was particularly interesting because the reason why he came to see me actually is because he had noticed that he had recovered a fair amount, and he had done so while at the same time learning to paint because he had to figure out something to do. And he had now discovered that he couldn't play with the brushes while at the same time speaking. If he tried to do that, he would have a speech arrest. And I thought, well, that's sort of cool. And so we targeted that area, which lit up when he did both speak, as in this case, but also move the fingers. And it's the only area that you see lighting up that causes speech arrest. When blocked by TMS, he went into a speech arrest. But if you target this other area, the pars triangularis, that shows a lot of activity, and suppress that activity, he actually spoke better. So this was not contributing to the compensation or to the recovery. It was actually preventing, in part, the recovery. That's a serendipitous finding, but it illustrates something that, again, we've known for a long time. Konstantin Formonakov, some 60 years ago, or now close to 100 years ago, made the point, when you want to localize in the nervous system, there's at least 3 levels. You need to know where the lesion is. That's lesion localization, but that only tells you where the lesion is. That lesion has an impact on the brain. That's functional localization. But actually, that functional localization, that disruption leads to an adaptation, leads to a response by the individual, both physiologic and behaviorally, and that leads to yet another level of reorganization that he called symptom or disability localization, and made the point, in order to help patients, lesion knowledge is enough, No, lesion knowledge is necessary, but never enough. You need to get to symptom localization. That's his basic tenet. We have the tools to actually do that. And to illustrate that, let me again do an N of 1 experiment. This is a patient with a vivid, well-formed, sudden onset of hallucinations. She was describing that she was in the bathroom that morning and looked up and saw a caravan of elephants, little tiny elephants, very well formed, walking along the sink, and looked up and saw her face in amazement, looking at these things. Generally very non-stereotypic environments. And this is something that Jean Lermite described as peduncular hallucinosis. Last time I checked, there is no evidence that the peduncle does anything for vision, but he called it peduncular hallucinosis, but he did identify the fact that most people had, like this patient did, lesions in the thalamus. The patient came to the emergency room. The person seeing him her in the emergency room was Aaron Boas. And Aaron partnered up with Mike Fox, and they collected all cases in the literature with lesions leading to acute onset peduncular hallucinosis, and did a tradition, these are all the patients, and did a traditional lesion localization approach, and found out, just like John Lermite had said, most of them have lesions in the thalamus. Some of them in the peduncles, go figure. But if you look at the end, there are 23 cases, and the biggest overlap is 6. So one can sell it as this is the hotspot, but it's mathematically actually not tenable. It's like there is no hotspot. It's a crapshoot. You can have these symptoms from lesions all over the freaking place. And then Aaron and Mike did something that von Monachov, I think, would have loved, which is to say, these lesions impact the brain somewhere. Let's do the overlap of that impact on the brain. So can we do resting state functional connectivity of those lesions, do the lesion network overlap? And now there are specific regions that in 23 out of 23 individuals light up, become significant. And if you notice this one, a lesion releases of inhibition or something, releases the activity in those areas, which happen to be V5-MT, a visual area for motion, well-formed hallucinations is what they have. That gives you a symptom localization, and it also gives you a target for intervention. So if you use this to target, then you can resolve those hallucinations acutely in that patient. So we need to know exactly where that bottle is. We need to know and measure what impact it's having. We need to tailor it to the individual description and characterization of the symptoms. This is not easy to do, and it's sure not the way we normally do trials. But when you look at the results of trials with that in mind, it actually is quite interesting, and you learn a lot of things. So this is a very young Mike Fox, in one of his first studies with me, what we looked at is people with medication refractory depression who respond, where are we targeting, and how does it relate to other data of the functional connectivity on medication-resistant depression. We've heard beautiful structural data that map onto the same network. It has to do with the amount of anticorrelation between prefrontal cortex and subgenual accounts and explains the antidepressant effect of TMS. There is no a priori design to target a given spot in this data. It was simply where did we end up falling, and how does that spot we fell onto relate to the anticorrelation? The more it was mapping onto the anticorrelation, the better the response. But if you look at the individual subjects, this individual person, had a very strong anticorrelation that matched very well the group effect. She responded great. This person had the exact opposite by chance, did not respond at all. So Mike went and collected even more data, and you can predict from the anticorrelation whether the person was going to respond or not. And so building on that data and adding another layer of can we characterize the symptoms that relate to this, Sean Siddiqui has started to look at dysphoric versus sort of anxiosomatic symptom characteristics, finding out these slightly different locations in the prefrontal cortex that relate to slightly different locations in subgenual cortex, and showing that not only can you document that at population level, but that you can use that, quote, symptom localization approach to actually predict which symptoms are you going to target in a patient when you apply stimulation to that location. And if you build even larger data sets with more nuanced description of the symptoms, Drysdale has done so recently with a greater N of subjects, and you can tease apart even more of the specific symptoms that you can target with different locations. So this is at least three aspects that I think are important. Measure the effect that it's having, characterize the target based on the individual symptomatology and the network connectivity you want to target, and be able to identify the network, not only on the basis of the targeted spot, but on the connected distribution that accounts for the symptoms. Sometimes when you do that, part of the symptoms end up being linked to deep locations. And I want to finish with that notion. And again, use it as an opportunity to both recognize somebody and highlight how you all need to speak up and be resilient. So Nir Grossman got a welcome grant to come work with Ed Boyden and myself. And we were excited, and he was going to do optogenetics of brain stimulation, and we thought that's going to be awesome. And Nir got to Boston and said, I can do that, but I have a better idea. We thought, I thought you got funded to do this, which is a cool idea. He said, yeah, but I think I have a better one. I think if instead of using just one path of stimulation, we use multiple paths of stimulation, and they collide at some point, we can leave residual selectively in the depth. And I thought, boy, he is on something I want to be on. That's a great idea, but that's not going to work, because haven't you thought of the dispersion and of the problems you're going to encounter, and how are you going to really ensure it? He said, no, I'm aware of all that. It may never work, but can I try? And we said, sure, try. And so with that idea in mind, Nir developed what became known as temporal interference. So the idea is that you can put a field of alternating current that is very high frequency, 20,000 hertz, and collide it against another field equally high but anti-phase, so that when they collide, they cancel each other out. One is 20,000, one is 20,000, and a little differential, 20,010. And so when they collide, the 20,000 go away, 10 is the residual that is left. Where? At the point of collision. So if you can geometrically target it to hit the hippocampus, you might be able to selectively activate the hippocampus. And so he went on to do so and show you can selectively activate the hippocampus here in CFOS. You get nothing if you just do 20 hertz. You get very little if you do any other form of stimulation that doesn't have the carrier. And so he was very excited, so were we. And we said, yeah, it's because it's a mouse. It's never going to work in a human. And Nir said, well, maybe we can find somebody who can take the challenge to the next level. And we did. And Inés Violante has completed recently a study in humans, first in cadavers, then in resting state fMRI, then in behavioral manifestations of encoding and retrieval of episodic hippocampal dependent tasks, showing that you can selectively target and modify subfields of the hippocampus in humans without affecting anything else. Unbelievably cool, I think. These are healthy subjects. These are young, healthy subjects. Can that translate into pathology? How much disruption will there be for amyloid and tau? Can we, in an older brain with more atrophy and therefore more cerebrospinal fluid, still get selectively? Does it work in the hippocampus because it's augmented by oscillatory pathways and will never work in the accumbens of the amygdala? I have no idea. Okay. But I hope this is exciting enough that a lot of you guys want to look at it, because I think it promises the possibility of selectively targeting deep brain structures in ways that can be combined with superficial structures and have a real impact on networks in a opportunity to translate to clinical applications, but also to understand fundamental aspects of brain. One truly last point, if I may. If you have this type of tools, you can then apply them guided by the individual level and send them home with it to do it at home. And that I think it's a really exciting opportunity. This is work from Davide Capone and among others, Lucy Bresset, showing that if we ask subjects to do an episodic memory task, without going too much into the details, there is a very different spatio-temporal signature of activity in older, healthy, cognitively intact adults versus patients with MCI. You see the same altered pattern in people with Alzheimer's disease without cognitive deficits yet. One such person is shown here. This is somebody I had followed for a number of years. Got to a point where he was procedurally doing fine, going and playing golf, but couldn't remember who he played golf with, how he got there, who is this lovely lady that picks me up, his wife of 50 years. With brain stimulation targeting this abnormal spatio-temporal signature to restore it, he went from a memory index of 0 to a memory index of 15 in 3 months. And it's not one person alone. We did a group study showing that consistently you can induce that change. That may or may not be great. You can improve them. Now, how do we sustain it? Maybe a almost ethically more challenging thing. But the point is that the causal relationship between that pattern of activity and the behavior, at least, seems to be established. And it's specific for gamma-driven activity. It's a signature that has a spatial distribution, but also a temporal distribution, and the source of which is in the retrosplenial cortex. And so you can localize the retrosplenial cortex, and if you target that in a gamma frequency TACS, Alberto Benussi has done so, then you can show that by as much as you increase the precuneus mediated gamma activity, you improve the cognitive function in these individuals. Now, the exciting thing is that, as I was saying, by changing the pattern of activity and the symptoms, you can ask the question, does it change the pathology? And Julia Sprugnoli and particularly Meva has done work showing that it not only improves the symptoms, but reduces the amount of amyloid and tau deposition on the PET scan of these individuals. Super, super early. This is literally all the data we have, and N of 4. So take it with a humongous grain of salt, but at least it gives us the tools to start asking this kind of questions, which, when enabled, allow you to target more than one circuit at the same time, because you can now define different locations and go after them in a systematic way, which is the work we're doing currently with Brad Manner. So to wrap it up, I think we have tools to really offer novel insights into brain behavior relationships at this concept level of circuitopathies and spatio-temporal signatures, using brain simulation techniques as a sort of toy model for the perturbation. And in doing so, we can not only understand fundamental new insights of brain behavior relationships, but ultimately develop personalized home-based neuromodulation approaches to address enormously disabling illnesses. Thank you. Sorry.
Fantastic. Thank you so much. And I'd like to invite Kelsey Cox and Estelle Higgins up to the podium to begin the questions.
Thank you so much for your phenomenal tour de force. It was really incredible. Something that we are doing at the Center for Healthy Minds is, or at least my work, is looking at the relationship between the brain and the body and inflammation specifically. So something that I'm wondering is, do you foresee this neurostimulation ever being used or broadened to modulate the brain in order to modulate peripheral responses, such as like acute inflammation, or even, in healthier populations, just trying to augment well-being? And are there ethical considerations there?
Oh, that's a great question. So I have to confess that my belief, maybe my bias, is that the brain spends more time monitoring the body than it does monitoring the external world, right? And that cannot be a chance occurrence. There has to be a reason for it. And I'm one of those who believe that has to do with interoception and salutogenesis, the possibility of actually promoting health. And we know that sometimes it's not salutogenesis that comes out of it, but actual pathology that you develop illness. If that is true, then identifying those networks that map onto those effects should give us a target to promote that salutogenic effect. And I do believe in it. I don't know that we know those networks yet, but I think that there is a lot of literature. In fact, there is really classic Russian neuroscience literature, or books on it, as to what are the brain circuits that map onto the liver and the biliary gland and so forth. And I think we now have the tools to really systematically explore that. And so good for you to do that. If it works, then I think it has to be because of modulation of inflammatory cascades. And I presume that that's the mechanistic underpinning. So I think there is a lot of value in exploring that systematically, and I'm a big believer of that.
Thanks. Yeah. Excuse me. Thanks for the talk. I was curious, like, to optimize treatment outcomes for patients, it's important to see enduring effects. So I was wondering, are there data to speak on long-term effects? And would something like multiple treatments over a long period of time be necessary? And then what kinds of effects could this have on patients regarding like safety or tolerability?
Yeah, thank you for that. That's a wonderful question, and I think, if I may, there are at least three aspects that I would love to comment on. One is that we can do things that oftentimes I think we should not do, or at least we should question whether we want to do. To give you an example, I had a few years ago a discussion with a colleague in an editorial board, because I got a paper to review of using brain stimulation to induce plastic changes in healthy, normal subjects. And I said, well, that's a little daring, isn't it? Did they really understand what the issue is? And the study doesn't show that those changes were reversed. So I actually have a problem with this. So I think there's some things that we can ask that it would be really good to know, but that we should at least wonder whether and discuss whether we want to go there. So that's the first thing. So to your ethical one. The second is that I think the duration of the effects that we get, it varies depending on the subject, but also depending on the condition. So, for example, in the case of depression, we know that in order to induce the changes that have therapeutic meaning, you need multiple sessions. With one session, you don't get enough. Nolan and the Stanford group has now shown you may be able to pack a lot of sessions in a short period of time, which is great, but you still need a lot of sessions. And when you do that, you get months of benefit. We know that you can repeatedly apply the simulation, as I mentioned, and maintain it. That's great. In an animal model, where you can go a lot longer, we showed that ultimately there is a plastic change with structural underpinnings that sustains the effect for longer. But what does that mean in humans? Does it ever happen in humans? And if so, is the net result beneficial or not? Is a question. So I think it becomes important, again, ethically to disclose appropriately what we know and don't know, and not to go sort of too overboard and too wild with it. In other situations, the effect appeared to be very short-lived, but enables somebody to do something about it in a different way. There is a book by John Robinson, actually describing an experience of participating in a research study of Lindsay Oberman's in my lab, and he has high-functioning autism, and the study had to do with disrupting in an acute session mirror neurons to see if empathy was modified. It very, very controlled, not therapeutic, just very controlled cognitive neuroscience. And John describes that after that experiment, the condition, which he did not know that it was blinded, we were blinded too, but when the condition fell onto the right location, quote unquote, he had this massively different experience of all of a sudden be able to read into people's faces and eyes and minds what their feelings were, or he thought so, which he had never experienced before, and he completely changed his mind. And the way he puts it is, I had never realized that the sky is blue and the grass is green. This intervention allowed me to do that, and then it was gone. It was still in black and white, but now I knew what blue was and what green was, which before I didn't. And it led to a behavioral change that he describes in the book that ultimately he feels, quote, cured him. TMS did not, but it enables maybe something to do. So I think your question is very good because it's very nuanced, and I think we need to figure out for each indication and condition what the answer is going to be. My guess is that it's going to be different.
Yeah, one other question that I was thinking about in just talking about how sort of all of these effects are within a circuit or multiple circuits. What do you think the next steps are for identifying, is activating one node in that circuit more beneficial than another node, or co-activation of multiple nodes could have more enhancing effects, and what's next?
Yeah, cool, right? There's so many questions to ask. I mean, I don't know. I don't know what the answers are going to be. I have the intuition that one node is going to be less effective if we target one node than if we, in a controlled way, target multiple nodes with the right parameters, whatever those are. So that becomes an experimental question. Not only that, but also target the connectivity, the timing of connections between different nodes, right? So to mention two concrete experiments, Emiliano Santornecchi did a study showing that if you give people a very, very complicated, quote, creativity, fluid intelligence task, you can show patterns of activity in gamma band, particularly posteriorly parietal regions, and in alpha band in frontal areas. And if you target these different nodes at the right frequency, you get an improvement in the individual performance in the task, or an improvement in creativity. But if you target the wrong nodes, control areas, or the wrong frequencies, you disrupt it. So there might be an opportunity to explore the parameters in a more nuanced way so that you target multiple nodes of a given network at the right frequencies. Did another study looking at frontoparietal network and in training the connectivity. So not modifying the activity in the node, but modifying the connectivity itself. And that had a dramatic impact, right? So that I think oftentimes we think of just modifying one node and having a network effect, but if we start getting more nuance in what we know about network neuroscience, we can develop more effective probably intervention. Certainly more effective intervention to test the notion that that network is related to the behavior. The answer may be whatever it is, but that's why we do the experiments.
Thank you. And then I had another question about what are the potential barriers for like a more widespread adoption of these non-invasive techniques? And you kind of talked, excuse me, on it a little bit before, but considering its non-invasive nature, do you foresee the use of this, excuse me, sorry, beyond clinical populations, so like in healthy individuals to boost cognitive function and the ethical considerations around it?
It's a great question. So there is a whole do-it-yourself movement. You guys probably know. You can Google what do I need to buy to make myself a brain stimulator, and $100 later you have one. And I've seen a number of people of that movement, in part to engage with them and learn from them, in part because of problems that they develop. I saw one of them because he had become convinced that the stimulation can be particularly focal if you have one very small electrode and a reference electrode in the subclavian fossa, and he had gone on to burn himself to the point that he had a 4-centimeter deep ulcer in the subclavian fossa that got infected. I mean, just disgusting. You know, so I think there is real dangers in the do-it-yourself movement, and we wrote an open letter to the community saying, you know, I think it's great. I'm quite libertarian, but you should be aware of the potential risks and all the knowns and unknowns that we have, and be aware of what you're potentially incurring. So I think there is a need for some form of regulation around there, or at least some form of support. That said, I think there's also at the other end that these are very, very complicated, very expensive experiments, right? I mean, we do resting state MRI and high density EEG and integrate them both and do multifocal stimulation. That is not easily scalable. But I also don't know that we need that for a clinical effect. You know, it's just it's an experimental question. It's an open empirical question. How much precision do we really need for the therapeutic effect? It may be that what we need can be as simple as 2 electrodes, and you can do this anywhere. And maybe consistent with that, there are therapeutic effects that we're seeing and that are being reported with a lot less technically sophisticated approaches. But I think we need this kind of more control approaches to find out the answer, essentially, and figure out how scalable these are.
Let's turn it over to.
Hi, thank you so much for such an interesting talk, and I think a really compelling philosophy about how we should be approaching understanding these diseases. I'm wondering about how we might try to apply this approach to diseases that are like very complex in their symptomology, like depression, which may be, you know, perhaps a whole brain or a whole body disorder, and whether or not, you know, we should be isolating symptoms and trying to identify that node, or if it's worth sort of taking a step back and trying to capture something more complicated.
Yes. It's a great question, and I struggle with that all the time. I don't know the answer. I think that the approach I have taken is to try to argue, maybe excessively, but consistently at least, that these are not treatments for a disease label. This is not a treatment for depression. It's an intervention that can have an effect on, tell me, what are the symptoms that you have that you would want to get help with? And let's figure out whether we can target that. That may be overly simplistic. I think that works, by the way. So we can do that, empower patients to define, capture well the symptoms with this kind of metrics, identify the neural substrate and target it. It works. Of course, it works just like we know for a long time, very pioneering work, that we can take away auditory hallucinations in people with schizophrenia, and they are equally schizophrenic, equally disabled, except now they don't have auditory hallucinations. And so how do we identify the symptoms that are really critical, that make a difference? That is a challenge in itself. But at the same time, there might be much more fundamental approaches that we've become increasingly interested in. For example, the work from Rubén Perello that I shared, he then went on of the resilience to the stress. It turns out it maps onto the target that has been shown to be relevant for resistance to Alzheimer's pathology. And so with Rubén and another fellow, Gabriele Cataneo, we started to look at, can we increase, quote, resilience or reserve or in people with dementia and make the pathology slow down, as it were. I don't know the answer, but we have a study going on to that. So there might be approaches that are more fundamental for a given disease, but the way I've been thinking about it for now is empower the patients to help us define the one or few symptoms that are critical. One last comment is that oftentimes you can target more than one symptom. So executive function and memory, you can target both circuits independent from each other and show that by combining it, you get more effect.
Thanks, that was terrific. I wonder if you could either clarify or restate some of the data you showed at the very end with increasing gamma in the precuneus seems to remarkably increase memory. What is your hypothesis, or how do we know, or what do you know about how that intersects with the more classic memory networks, medial temporal lobe or whatever, in terms of how that's working? What do you think?
Yeah, so there is a parallel line of work from the angular gyrus to hippocampal connectivity showing that posterior connection has a critical node in the retrosplenial cortex. So that I think what we're modulating is essentially the same network that Voss is talking about and that Reinhardt is talking about in Boston, targeting different nodes of the same posterior connections of the hippocampal network. That's why I think it works for memory. What is a little surprising to me, and I mean, again, we do the experiments because we have other theories. So my hypothesis was that theta was going to do the effect and gamma was not, because I assume that gamma is critical at the hippocampal level, but is gated by theta at cortical level. We didn't see an iota of a theta effect, not clinically, not physiologically, and it was driven by gamma. So that I don't know, but the spatial distribution appears to be that same one that they've been showing with functional connectivity, for example.
Before I ask my question, I just want to remind folks who are online that they can also ask questions. So please do. And I wanted to ask something. First, Alvaro, thank you so much for not only the talk, but all that you've done to help us understand and promote this area. This is a multi-part question. We found increased gamma oscillations with certain kinds of meditation. One of the things we found is that these effects are not present just during the state, but also persist outside the state. And there are robust differences at, quote, baseline that differentiate. And so one question is the extent to which the neuromodulation designed to increase gamma oscillations, to what extent does that affect baseline resting activity? And the second question, which is related to this, is that there's a conjecture that I don't think really has a lot of evidence to support it at this point in time, but there's a kind of intuition that strategies that require some effort and self-regulation, that, if you will, are endogenously driven strategies, may lead to more enduring effects on the brain than strategies that are exogenously imposed on the brain. Now, I'm not sure whether that's true. That's just a conjecture. And I wonder what your thoughts are about that with respect to neuromodulation in general.
Yeah, those are both great questions. The first one, I think we're struggling to answer. I think it's really important to know how long-lasting are these changes, and how predictive is the baseline that you have of the results. And there is at least a hint that that there are baseline differences that would allow to predict who is more likely to respond. And then the effects that we see are very dramatic during the stimulation and immediately after, but there is a long-lasting trace of that. And so I think we're going to find that there is an induction of a change that sustains and that probably drives some of the behavioral effects. The question of whether endogenous or not, I always worry that by asking folks to modify behavior or to do certain activities, we introduce so many degrees of freedom that it becomes very difficult to coordinate, right? So my experience with this started with Stephen Coslin when we were trying to figure out imagery, and long story short, we did this experiment asking folks to imagine themselves playing the piano, and if you told them you're a camera watching yourself, we got nothing. If you told them, I have no idea how you're going to do this, but imagine the feeling of your playing, we saw dramatic changes, right? So exactly the instructions are going to matter a lot, and I worry how people hear those instructions and what actually turns out to be. And so in a sense, call it laziness, but I think it becomes a lot easier to control that perturbation externally. And I know I can induce gamma in your brain at this location, 100%. It may translate into behavioral change or not, but I 100% know I can train it without you being able to fight it very much. If I engage the state that is appropriate, I probably can do more so. And so my guess is that there's going to be some combination of both approaches at the end.
Thank you again for your talk. So I'm Mel Carrasco, I'm a pediatric neurologist here. I really appreciated your discussion. I think it was Grossman's and Violante's research on selective targeting. That spoke to me because I know we're not anywhere near where we could apply some of these concepts maybe to children, but I live in a day-to-day setting where I find myself not only just treating the child, but trying to convince the parents to do certain therapies and being able to selectively, I don't know, I feel like that would help me convince more parents to do this sort of thing. How do you see the field progressing towards including children in the future? Thank you.
Thank you. Thanks for what you do. Good luck with the parents. We're tough. So look, I think the dream in my mind is that a lot of the things we're doing invasively now, we will be able to do non-invasively with these techniques, right? And that would be amazing because it would allow more flexibility, more targeting, earlier intervention, all this kind of stuff. I think we're far from there. I think there is a lot of questions, including questions of the age effect, right? So as you well know, GABAergic neurons have a very different pattern of induction, physiologic effects in children than in adults, and it's not quite clear when the change happens. So when exactly can we bank on a given parameter having excitatory versus inhibitory effects? Even that is completely open. So, and myelination patterns will probably impact this, and so I think there is a lot of questions to sort out. But at on the other end of the equation, the smaller brain, the more pervasive, transparent brain, less CSF, all that is actually bodes well for more precision targeting in children. So, so immature brains are probably more likely to have appropriate induction where you predict it from the modeling. That's what the modeling data would suggest. So I think it's exciting, and I think the part of the problem, very practical, is that IRB approvals for this intervention in children are tough to get. I think appropriately so from the ethics committee point of view. So it requires, like you're saying, a risk-benefit argument that that is very clear-cut. This is rare diseases, limitation of support, and a poor prognosis. Let's try this. So the question is, what do we know about developmental studies, preclinical developmental studies that may be relevant? So part of what we know is that so at least three things that are relevant that we know. One is that the physiologic responses to the stimuli, because of the effect of some of the neurotransmitter in the developing brain is very different in the child in the developing brain than in the adult brain. So that we know. The second thing that we know is that the amount of myelination and the strength of the thickness, as it were, of the paths determines a lot of the current flows. And so if you do the modeling in a child brain versus an adult brain, it's not just size that conditions the distribution of the current. And the third thing that we know is that because tissue characteristics have very different conductivities, CSF amount in the tissue determines a lot of shunting and distribution of current. And that is very different in a child or in a developing brain than in an adult brain. So it becomes a bit of a different thing. It's not stimulation in a smaller brain. It's stimulation in a different brain. It's something that pediatricians have long known, but that I think we need to adapt to this. So in regards to these measures, so the question is about what do we know in regards to plasticity? And in regards to these measures, what we find is that the efficacy of the mechanisms of plasticity linearly goes down. So you know, we've done studies now from age 2 to 80 plus, and it's not that you get a ramp up and then a plateau and then a ramp down. It's a pretty linear downward for every connection. And connectivity, on the other hand, has a very different pattern. So if you look at the impact of the stimulation distributed, you get a system that is, if you want to think about it, noisier with age, that has more distributed impact at longer distance. So it's less focalized in its disruption. So you get both a greater modification locally and a progressively less modification locally, but more distributed impact with age.
Okay, just a quick question. So I just want to share that I thought your talk was like really not only fun, but really, really inspiring. Thank you.
Thank you.
So I'm curious whether you think it's either plausible or whether you're aware of anyone that's tried to not only use either neuromodulation or stimulation to stimulate or modulate, say, a particular functional network of activity like you talked about, but to try to, I guess, facilitate or potentiate plasticity. Maybe like essentially to potentiate a capacity for neural adaptation that would essentially make some network or the brain more responsive to experience or perhaps to some other parallel form of neurostimulation.
That's a fantastic question. I love that. As Richard was saying, I think I've devoted my career sort of led by notions of plasticity and how to explore it, how to leverage for translation. And so along those lines, we initiated lines of work that have been followed by many others, trying to do, I think, something a little bit similar to what you're saying, but not so much actively inducing change, which I thought was not going to work, but rather suppressing activity in specific areas and hoping that by doing that, the brain figures out a different way. So in my very simplistic way of thinking, you've gotten used to coming down a given slope on your skis, and I'm going to block that path so that you need to figure out a different way down the slope. I don't know how you're going to do that, but the brain will figure it out. That sort of idea. And we applied that mostly as pre-rehab. So we've done a number of studies as acute intervention, basically identifying the network for language or for motor control that ends up being impacted by a potential tumor and will limit the resection of the tumor, and then using stimulation coupled with training to force that person's brain to come up with a different strategy because you're suppressing one key node because we want to promote reorganization. That works. Actually, it does reorganize within weeks, and it has allowed for larger resections in very, very small series, ends of 2 to 12. So very small studies, mostly around motor function and language function. So limited application, limited end. But if it works at that level, it lends itself to the kind of question that you're saying. And of course, some of the things that are approved for TMS, effectively, I would argue at that, right? So if you think about, not that it's applied this way, but what is approved by the FDA, cleared by the FDA for obsessive compulsive disorder, is essentially a provocation strategy to come up with the obsessive thoughts and then disrupt it. And it's not applied that way. Generally, it's applied just as stimulation in the hope it's going to work. And the FDA has so far not had an issue with it, and insurance keeps paying for it. But that's different than what actually was done in the studies, which is more along the lines of what you're saying. How can we engage behavior in such a way that we promote, with the stimulation, promote some reorganization, accelerate that process? I think there's a lot of opportunity there to explore further, but I think it's going to be fruitful. What do I know?
Thank you for an amazing talk. No pun intended, extremely stimulating. And yeah, I'm extremely naive to the methodological intricacies of TMS. But I wanted to ask a question specifically about the functional localization step. So you used functional connectivity, resting state functional connectivity to define the functional parameters. And as you already know, there are lots of ways of calculating functional connectivity. Functional connectivity patterns are specific to specific temporal bands. So I'm just curious, is this, in terms of functional localization, is this just a greedy search problem where we try out lots of different types of functional connectivity to find what's most effective? Do you have any intuitions about methodological choices we could make when calculating functional connectivity that might get us closer to the answer without having to try all the options available?
Yeah, that's a fantastic question. I think at this point it's a trial kind of approach. Oh, look, this is a really cool picture. 23 out of 23. That must be the answer. So I think we're very naive in that sense, or very early in the process. I don't think it's naivete, but very early in the process. I also think that oftentimes the preconceived notions that we have of what is the way to do it, I think are going to prove to be wrong because our preconceived notions were wrong to begin with. So I think we need large data sets to allow ultimately data-driven approaches to tell us the real answer. That's my core intuition. Until that point, I think that being aware, I think all pretty well that structural connectivity is going to constrain to some degree the functional connectivity, and that if you do not only resting state connectivity, but do DTI and merge them and combine that, that will get us a lot more effect, that if you take into consideration local versus distant connectivity patterns, that ought to be very relevant. So I think there are things that we know will make a difference, and there are folks that are trying to do those kind of approaches, obviously, and I think we're going to see a rapid change in what is quote standard to apply.
Thank you. I was in the interest of scaling the applications. I was wondering, what do you have to say about EEG source localization? Is it very far away from, in terms of the accuracy and being able to target specific locations? Any comments?
Yeah, so the struggle I have with my training, my PhD is in neurophysiology. So I wish that I could tell you source localization is it. This is the way to do it, and this will give you the location. I've become less and less convinced that we're going to get there for the very same reason that we were discussing with imaging. There's so many ways to constrain and define your analysis that we end up being good at making it look sort of nice. But that's why I like Don Tucker, I think was the first one that made the point. Look, if you have essentially receivers and you have a source somewhere, I don't care where, but you have a source somewhere and you're picking up that activity from that source in all the receivers. And there's going to be a scale factor that you can calculate. So you may not know exactly the source, and you may not need to solve the source localization question, as long as you can inject current with the same scaling distribution as you had before. And so that is a little lacking of the satisfaction of saying, oh, it's coming from here, but it has the potential of actually avoiding some of the challenges that come with wanting to define the location. So it's more at the level of functional resolution than anatomical resolution, but I think it's not a bad idea to approach it that way. That said, I think that EEG for the scalability question, I'm a firm believer in that has, and I think part of what we need to do is figure out how few localization sources do we actually need to guide the intervention in a closed loop way ultimately. So I think ultimately we're going to have devices that build in the recording, the reading, and the writing, and well enough that it gets you the behavioral effect.
Thanks for a terrific talk. I have a ton of questions, but I'll just limit it to two. One is about the perturbation biomarker related to predicting cognitive decline. And I was wondering if that could be a proxy for just, white matter connectivity between those regions. Could you get the same information if you were to just do a seed-based resting state functional connectivity? So that's the first question. The second question is more of a clinical question, and wondering whether, getting a resting state scan, should that be part of the clinical treatment protocol or the evaluation for clinical treatment? Because I was really struck by your slide about the variable response to different frequencies of stimulation, and flashing to a patient who had TMS done and felt terrible afterwards.
Yeah. So I mean, in terms of the first question, so Kilian Avellaneda, who did that study that I was showing, his training was in imaging, and so he actually looked first at the functional connectivity and the structural connectivity, because he said we don't need TMS for anything, which was great because it didn't work. But it's really important controls, and so I think there is something special, whether it's effective connectivity or whatever we want to call it, but adding the perturbation was critical in seeing that effect, and at least for this small n. It's a small n study, right? But for that small n, it made the difference. My guess is that sometimes one may be okay with just a structural connectivity. More often than not, it's not going to be enough. That's the impression I have, and that adding the perturbation will be more predictive of the outcome. By the way, we found the same thing in predicting the risk of delirium just the connectivity from EEG, just from EEG alone, is predictive of the risk of delirium. If you add the TMS, more Shafi showed, the response to that perturbation is a much better predictor of the risk of delirium. So I think there is something to it. I believe it. So that's for the first. The second part of the question. So I'm going to answer it in a provocative way, if you allow me. He's a friend, so I forgive me, Nolan. But the SAINS protocol, right? So the Stanford Accelerated TMS protocol is predicated on the hypothesis that underlies this. In fact, leverages that IP. It made the point that by knowing the location of maximal anticorrelation, you can target that area. And they did this study and had spectacular results, and never analyzed the data based on the connectivity. And so I called Nolan up and said, the hell? I mean, you never tested your hypothesis. I mean, it's just a spectacular hypothesis. I happen to believe it, but is that okay? So you're smart, so I'm taking it to mean you tested it and it didn't work out. And Nolan said, I can't comment on that. But I think it illustrates the fact that oftentimes the hypothesis is a great way to test an idea, and then the results are what they are. So I don't know how much this needs to be part of clinical routine. I do think that at least where we're now, it should be part of clinical trial, experimental approach, so that we can answer the questions, because otherwise we're assuming we have a sense of what is going on, but we really don't.
Hi, thank you. I'm curious, in the context of TES specifically, with epilepsy, do you know anything about the outcome and the data from that?
Yeah, I do know a little bit about it because for disclosure, I'm an advisor to Neuroelectrics, which is the company that is doing the pivotal study. And the initial trials that led to that pivotal study were done in my lab. So there's now there's an ongoing pivotal study. Those results I don't know. It's a double-blind study targeting epileptic foci that can be well identified in pediatric all the way to adult populations in individuals who are not surgical candidates. And in the studies, a 2A, a 2B, and a sort of small phase 3 trial that was done leading up to that pivotal study, the results were really, really good, as long as you could really localize the seizure focus. And that is a big question of scalability, right? So these were folks at very high-end epilepsy programs generally with PET studies and with the neurophysiologic monitoring, and because of the pre-surgical sort of process. When the seizure focus was not well localized, it happened in 2 instances. Not only did the kids in that case not respond, but actually got worse. The seizure activity got worse. So I have the impression that the results of the trial are going to be positive. I hope so for the company's sake. But the studies leading up to it were quite positive if the seizure focus can be localized. But the fundamental principle is to target, as you know, the TES in such a way that the cathode is targeting the seizure focus area, and that we know that reduces firing probability of those neurons. So that's basically what it does, is cool down, similar to a cooling probe, the seizure focus.
So, thank you, Alvaro.
I do want,
Oh boy,
thanks. Okay, I'll be quick.
this is going to be painful.
So this will be painful. So I wanted to ask you about the unblinding problem and how you think about this now. And does TMS or TACs induce particularly strong expectations? And yeah, what's the state of the art now?
That's a great question, Tor. Thank you for that. I think with both TMS and TDCS, there is really sort of pretty nice data Matt Burke and others showing that there is an enhancement of placebo effect. People sort of like the techiness of it, and there is not only is there a placebo effect, there is a rather prominent placebo effect, and so that needs to be taken into consideration, making the need for appropriate controls really important. With TMS, there are technological solutions that you can implement to have coils that essentially cancel the field out. Basically, if instead of having the current go in the same direction in the center of a figure-8 coil, they go in opposite directions, then in the center there is a net zero field done, but the perception is the same. So what happens is that those are not commercially available coils. So there is some limitations in some of the trials, and what is available is not perfect. But the companies are well aware of it and are trying to develop it. For the TACs and TDCS, actually the solution there is quite straightforward. You can generate a field that feels exactly the same, that is limited to the surface by having electrodes close by that cancel the depth penetrance, that shunt the current, basically. And Neuroelectrics, among others, has published on algorithms to tell people how to do it. And that works really quite well. People are convinced that they're getting the real thing, even experienced people. I mean, so I've put it on myself, and I was not able to tell which one was which, simply by having more electrodes. What it does require is having montages that are multi-electrode montages in everybody, in the real and the sham condition, the same number of electrodes, but only activating some in different ways. Yeah, in TI, you can't tell. I mean, TI, you feel nothing. Maybe because this 20,000 hertz just goes right through, and you really can't tell that you're getting stimulated, except when it comes close to the eye, that the residual, the 10 hertz or 20 hertz activates phosphines. And so you get the retinal phosphines, which Edwin Mark showed a long time ago. So that you notice. So you need, again, what you cannot tell with TI is whether the beams are going to interfere in the hippocampus or slightly off. And what Ines did was show that if you target the anterior component or the posterior part of the hippocampus, you get differential effects. So you can create really nicely controlled experiments for that. It's a very important issue.
Well, hopefully this is a hopeful question. Thank you so much for such a stimulating and just invigorating talk. So there's now FDA approval for the first treatment for Alzheimer's disease, which seems like the optimal place to bring in TMS, since they have to go regularly for infusions into the clinical, hospital setting. Are people already testing to see whether the combination of TMS with the anti-amyloid infusions is increasingly protective, or using such a motivated and captive subject pool to actually test in terms of a participant population?
That's a great question. So I'm not aware of any studies that have looked at the effect of lecanemab on cortical responses to TMS, or measures of plasticity, or whether you can increase the effect. That'd be a really interesting question. I think one of the challenges of lecanemab is aside whether you believe or not in the Alzheimer's link to amyloid theory, but the practical challenges is that probably less than 8% of patients with early Alzheimer's are actually going to be qualified for lecanemab, right? And so there is a real challenge in getting people to get it. And so the N is much smaller than the actual population of patients. And engaging those people in additional studies that may potentially change the efficacy of the intervention or the risk is going to be a really tough sell to IRBs. And as a clinician, I'd be hard pressed to convince a patient, let me do TMS on you, and if you bleed, well, we'll call it a chance occurrence. I think it'll be a tricky challenge. So, but it'd be a really interesting question to answer. Whether I do believe that neuromodulation has a value to add to dementia in general, and I do believe that combining with pharmacology is the way to go. You know, cycloserine, ketamine, there memantine, maybe in the case of Alzheimer's. So I think there is a lot of opportunity there.
So, thank you so much.
Thank you. Thank you so much, both of you. Thank you. Thank you so much.